Hello and welcome to our module on sound. We are going to start out by talking about vibrations and waves, where waves are a very important physical quantity, not only talking about waves in the ocean or waves from sound waves, but also, as we saw in previous chapters, electromagnetic radiation is given by waves. In addition to this, there is also the wave properties of matter, which become important when we're talking about quantum mechanics, which, as I've said before, is the fundamental underpinning of chemistry. To begin with, we are going to talk about harmonic motion, with the most obvious case of harmonic motion, or at least the most well understood, being the motion of a mass attached to a spring. If you'll remember from our discussion of Hooke's law, the force from a spring is going to be equal to negative k times the displacement of the spring. What's going to happen is that if you pull a spring out and attach a mass to it, then the spring is going to oscillate back and forth because the force is going to be pulling it towards the center at all times. So at first in this diagram, it starts pulling towards the top, but as it passes the top, it still has its momentum going forward. So it's going to go a little bit past the midline until it is slowed down and then pulled down. And then it's pulled up and pulled down and pulled down up and then pulled down over and over again in this shape that we call a sinusoidal wave. This diagram gives a few definitions for a sinusoidal wave where the amplitude is the distance from the highest point or the lowest point to the midpoint, and the wavelength is the distance that it takes in order to start repeating itself. I have a bit of an issue with this diagram in that the wave only moves with respect to time when you oscillate a spring, not with respect to distance. So the wave wouldn't actually be moving to the right. What we would see is that this would be the shape that came out if you graphed the motion or the position of the mass versus time instead of the position versus distance. That's important because the wavelength is generally the distance that it takes for something to start repeating, whereas the period, which we are going to define in the next slide or two, is the time that it takes for something to start repeating. These are some sinusoidal definitions. The amplitude is the height of the wave. The wavelength is how long in space it takes for a wave to repeat, which is measured in meters. The period is how long it takes in time for the wave to repeat, which is measured in seconds. The frequency is how often the wave repeats, 1 over the period, measured in 1 over seconds, or to give it a more formal name, hertz. If the pattern repeats twice in a second, then that means that it has a frequency of 2 hertz. If it repeats 3 times in a second, then that means it has a frequency of 3 hertz. Whereas the period for this would be 1/2 of a second and 1/3 of a second, respectively. Another type of harmonic oscillator is the pendulum, where a pendulum is a mass at the end of a long stick or string, which is pulled to the side and swings back and forth. So if you've ever seen a grandfather clock, the mass at the end, the stick and the mass that are on the bottom part of a grandfather clock are called a pendulum. Pendulums swing to and fro with such regularity that for a long time they were used to control the motion of most clocks. They can still be found in grandfather clocks and cuckoo clocks. Galileo discovered that the time a pendulum takes to swing to and fro through small distances depends on only the length of the pendulum. The time of a to and fro swing, called the period, does not depend on either the mass of the pendulum or the size of the arc through which it swings. A long pendulum has a longer period than a short pendulum. That is, it swings to and fro less frequently than a short pendulum. The period of a pendulum is equal to t, which is the period, which is equal to 2 pi times the square root of the length of the pendulum divided by gravity. The period of an oscillating spring depends only on the mass attached to it and the stiffness of the spring, which is called the spring constant K. not the amplitude. This period is then given by 2 pi times the square root of m, which is the mass, divided by the spring constant k. When we are talking about waves, it is somewhat important to know that we are not talking about a physical quantity, but merely a pattern. So, as a wave travels through the ocean, the individual water molecules do not physically travel with it, but rise and fall as the pattern pushes forward. So, an example of this that you'll see at many sports games is when people do the wave. So, as somebody does the wave, they lift their arms up and then bring them down. And then that pattern goes from left to right or right to left across the stadium, but the people themselves do not move. They are merely passing the pattern through, and that is what counts as a wave. The speed of a sinusoidal pattern is given by wave speed is equal to frequency times the wavelength. The wave speed generally only depends on the properties of the medium that the object is moving through. So there is a specific wave speed for waves coming out of your mouth and traveling a sound through the air. There is also a wave speed for waves which are traveling through a solid object. Like me knocking on the desk will produce sound that travels through the desk at a specific speed. There's also a wave speed of light and a wave speed of water, of a wave moving through water. Because this wave speed is constant for a material, what we can say is that as the frequency of a wave goes up, the wavelength of the wave must go down. Further demonstrating my point about waves being a pattern and not an actual movement of the molecules, except very, very slightly, is this diagram of longitudinal and transverse waves. So a longitudinal wave is a wave like you would press through a slinky, where you push the slinky forward, and that's going to cause the slinky to have an area of high density of coils and an area of low density of coils. This is called a longitudinal wave. You also have the more easy to define transverse wave, or the more easy to see transverse wave, which is where a wave will go up and down as it travels along the slinky. Both of these have a wavelength, which is the amount of space that it takes for the pattern to start repeating, but the waves themselves look quite different, as you can see in this diagram. There are also earthquake waves which travel through the earth, and waves that have been generated by earthquakes and that travel on the ground are of two main types: longitudinal P waves and transverse S waves. Geology students often remember P waves as faster push-pull waves and S waves as slower side-to-side waves. S waves cannot travel through liquid matter, but P waves can travel through both molten and solid part of Earth's interior. Study of these waves then reveals much about Earth's interior. Waves also have a property called interference, where as one wave adds to another, it can either reinforce or cancel out waves depending on whether or not they are in phase. So if two waves are of the same frequency and are totally in phase, then that means that they're going to have the same wavelength, and that wherever there is a high point of one wave, there's going to be a high point of the other wave, and wherever there's the low point of the other wave, there's the low point of the first wave. And when you add these two waves together, they reinforce each other and create a bigger wave, which is bigger than both of the waves that went into it. However, if they are out of phase, that means that one wave has high points at the areas where there are low points for the other wave, and then the first wave has low points at the areas where there are high points. Because of this, if they are of the same amplitude, then they're just going to cancel out and you're not going to see any wave at that position or at that point where the waves cancel each other out. So when you look at ripples in a pond from two different waves, you see these really complicated interference patterns, which are also going to be important when we talk about light. But we see these interference patterns where at the points where both of them have high pressure or high amplitudes of the waves, then they're going to add together. And at the points where they have low pressure or low amplitudes of the wave at the bottom of the wave, then they're going to subtract and reinforce each other in that way. But if you have it so that one part of the wave is interfering destructively, where one wave is at a high point while the other is at a low point, then you're just going to see these places where there's not any wave at all. One way we can use this constructive and destructive interference is in the creation of standing waves. One of the ways we can use this constructive and destructive interference is in the creation of standing waves. One way to create a standing wave is to tie a rope to one end to a wall, and on the other side oscillate the rope up and down. As you do this, you are pushing a wave through the rope, which is going to reflect backwards and then reflect from you and reflect back from the wall and then so on and so forth, creating incident and reflected waves which are going to constructively and destructively interfere with each other. If the distance between you and the wall is 1/2 integer multiples of the wavelength, so if the distance is half a wavelength, or one wavelength, or 3/2 a wavelength, or two wavelengths, or so on. If you do this, you're going to see that the wave is going to go up and down, but not side to side. Is that each half of a wavelength, there is a node which is always going to be at zero, no matter what, as the wave itself oscillates back and forth, kind of like this, or if you'll see it, it oscillates back and forth like the wave on the left-hand diagram. You can also make standing waves with two-dimensional objects or three-dimensional objects where instead of being a single point, the node instead becomes line. So if you place salt on a plate that's vibrating at certain frequencies in the X and Y direction, you'll see that the salt will go down to the nodes because the rest of the standing wave is going to go up and down while the nodes are just going to stay in their same place. And you'll be able to see these really complex node lines just looking at the position of the solid and understanding the principle of the standing wave. In this slide, we go over a couple of ideals, actually. The first of which is the Doppler effect, and the second of which is shock waves. If you have an object that is moving, in this case to the right, and releasing waves, then you will see that if the object is approaching you, if you are to the right of the object, the waves seem to be a lot closer, or the wave fronts or the high points of the waves seem to be a lot closer together than they would be otherwise, where each wave that's released is a circle. And as it moves to the right, the circles bunch up. But if you're behind it, if you're to the left of the object, it looks like the waves are spreading out compared to the actual distance between wave fronts if the person was just standing still or the object that was releasing waves was just standing still. This is called the Doppler effect, where the frequency or the apparent frequency of waves which are going to hit you if something is coming towards you is higher, whereas the frequency or apparent frequency of the waves of an object that's moving away from you is lower than it is in actuality. We see this in sound waves where if you have a siren that's coming towards you, then it will seem really high pitched or have a high frequency. But if you have an object that's going away from you or a siren that's going away from you, it will have a lower frequency. What we have with shock waves then is waves where the velocity of the object moving is greater than the velocity of the waves. So we see in B that as the velocity exactly equals the velocity of the waves, all of them overlap. But as the speed of the object exceeds the speed of the waves, you start to see this line or this cone where all of the wavefronts or all of the high amplitude parts of the wave are going to overlap, as you will see in a shock wave or a sonic boom, where if a plane is going faster than the speed of sound, it's going to create these high pressure areas and a low pressure area at the tail end, which are going to create a cone which goes out into three-dimensional space. And as the cone hits you, hear this boom. It doesn't necessarily even mean that it just exceeded the sound barrier as is known by common knowledge. A plane going faster than the speed of sound is going to release these, and you are only going to hear it once as the cone passes over you, but it doesn't mean that it just exceeded the sound barrier. All that means is that it is going faster than the speed of sound, not that it just started going faster than the speed of sound.